close your eyes for a moment and picture the night sky. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Now hold that image. Every star you can see, every planet, every moon, every cloud of glowing gas drifting between the stars, all of it together makes up less than 5% of everything that exists. Less than 5%. The rest of the universe, the vast, silent, overwhelming majority of it, is made of things we cannot see, cannot touch, and do not yet fully understand. Scientists call these invisible ingredients dark matter and dark energy. And tonight, we are going to spend time with both of them. Think about what it means to look up at the sky on a clear night far from city lights. The stars seem countless. The Milky Way stretches overhead like a pale river of light. It feels enormous. It feels like everything. And yet all of that glowing, burning, shining matter, every atom of hydrogen and helium and oxygen and iron in every star and planet and nebula we have ever observed adds up to just a small fraction of what the universe actually contains. The universe is mostly dark, mostly invisible, mostly unknown. That is not a failure of science. It is one of the most exciting discoveries science has ever made. Here is how the numbers break down. Scientists studying the universe have found that roughly 27% of everything that exists is dark matter. This is a kind of matter that has weight and pulls on things with gravity, but gives off no light at all. It does not glow. It does not reflect. It does not absorb light in any way we can measure. It is simply there, invisible and enormous, spread across the universe in ways we are only beginning to map. Then there is dark energy. Dark energy makes up about 68% of the universe. It is not matter at all. It is something stranger, a kind of pressure or energy built into the fabric of space itself, and it is pushing the universe apart, making everything in the cosmos spread out faster and faster with every passing second. We will spend a great deal of time with dark energy later in this episode. For now, just hold that number, 68%, more than 2/3 of everything that exists. is this invisible, outward pushing force that we cannot see or touch or collect in any laboratory on Earth. That leaves ordinary matter, the stuff made of atoms, the stuff you and I and the stars and the planets are made of, at just under 5% of the total universe. Everything you have ever seen or touched or tasted or loved is built from that thin sliver of existence. The rest belongs to the dark. Now step back even further. The observable universe, the part of the cosmos we can actually detect with our best telescopes, stretches about 93 billion light years across. A light year is the distance light travels in a full year, moving at about 186,000 miles every single second. 93 billion of those years. That is the size of the universe we can see. And within that almost unimaginable space, there are an estimated 2 trillion galaxies. Each galaxy holds hundreds of billions of stars. Each star is a sun. Many of those suns have planets circling them. All of that, all of it, is the 5%. The dark matter and dark energy that make up the other 95% are woven through all of that space, invisible and immense, shaping the way galaxies form and move and cluster together, and slowly, steadily pushing the entire universe toward a future we are still trying to understand. There is something deeply peaceful about this idea if you let yourself sit with it. The universe is far larger and far stranger than anything we can hold in our minds. The darkness is not empty. It is full of something real, something powerful, something that has been there since nearly the beginning of time itself. We are surrounded by it right now, in this room, in this moment, as you breathe slowly and let your eyes grow heavy. The universe we live in is mostly invisible, and learning to see what is hidden, to follow the clues, to trust the math, to listen to what the light is telling us. That is the story we are going to tell tonight. Slowly, gently, fact by fact, all the way to the edge of what we know. For a long time, scientists had no reason to think anything was missing. The universe seemed to make sense. Stars burned, planets orbited, gravity pulled things together, and light traveled outward in every direction. The math worked. The pictures matched the predictions. Everything seemed to add up. Then, slowly, it stopped adding up. The first hint came not from a telescope pointed at a distant galaxy, but from something much simpler. Scientists were measuring how fast galaxies spin. A galaxy is a massive collection of stars, gas, and dust, all held together by gravity and rotating around a central point. Much like water spinning slowly down a drain. Our own galaxy, the Milky Way, spins this way. So does every other galaxy we can see. Now, gravity follows rules. Those rules are very well understood. The more mass something has, the stronger its gravitational pull, and the farther you are from the center of a spinning system, the slower you should move. This is true for our solar system. Mercury, the closest planet to the Sun, races around it in just 88 days. Neptune, far out at the edge, takes 165 years to complete a single orbit. Distance means slower speed. That is the rule. But galaxies were not following the rule. When scientists measured the speed of stars at the outer edges of galaxies, those stars were moving far too fast. They were spinning at nearly the same speed as stars much closer to the center. By every calculation, they should have been flung outward into space long ago, like water flying off a spinning wheel. Something was holding them in, something with enormous gravitational pull. But when scientists looked for that something, they could not see it. There was no visible mass to explain the force. No bright cluster of stars. No glowing cloud of gas. Nothing. This was deeply puzzling. Scientists are careful people. They checked the measurements again. They used different instruments, different methods, different galaxies. The result was always the same. The outer stars were moving too fast. Something invisible was holding them in place. The simplest explanation was also the strangest one. There had to be more mass in those galaxies than anyone could see. A great deal more mass. Mass that did not glow, did not reflect light, did not interact with light in any way that our instruments could detect. It was there only in its effect. The way you can feel wind without seeing it. The way you can know a river is strong by watching what it does to the water around a stone. Scientists called this missing mass dark matter. The word dark here does not mean frightening or dangerous. It simply means we cannot see it. It emits no light. It absorbs no light. It passes through ordinary matter almost completely unnoticed. Right now, as you lie still and breathe slowly, dark matter is drifting through you, through the walls of this room, through the earth beneath you. It passes through everything, barely interacting at all, like a ghost that leaves no trace except the gentle pull of its gravity. The amount of dark matter required to explain what scientists were seeing was staggering. To hold galaxies together the way they are held, there would need to be roughly 5 to 6 times more dark matter than all the ordinary matter in the universe combined. 5 to 6 times more of something completely invisible than everything we have ever seen, touched, measured, or built. Every star, every planet, every moon, every ocean, every atom of oxygen in the air you are breathing right now. All of that adds up to only a fraction of what is actually out there. This was not a small correction to the math. This was the math telling scientists that they had been looking at only a thin slice of reality. The universe they thought they understood was just the surface. Beneath it, woven through every galaxy and every cluster of galaxies, was something vast and invisible and deeply real. It took time for this idea to settle into the scientific community. New ideas always do, but the evidence kept growing. Different measurements from different directions, using different tools, all pointed to the same conclusion. Something was missing, something enormous, and it had been there all along, shaping the universe quietly from the very beginning, while we looked only at the light. That is where the story of dark matter truly begins. Not with a dramatic discovery in a single moment, but with a slow, careful realization. The universe was not what it appeared to be. And the scientists who noticed this first were about to change everything we thought we knew. The story begins with spinning, not the slow, graceful spin of a top winding down, but the vast, silent rotation of entire galaxies. Hundreds of billions of stars, each one sweeping around a common center, like water circling a drain. This motion had been observed for decades. Scientists had measured it, recorded it, and believed they understood it. They were wrong. Here is what they expected to find. When you spin something, the parts closer to the center move faster. The parts farther out move slower. Think of a spinning record. The outer edge still completes one full circle in the same time as the inner part, but it has to travel a much greater distance to do it. That means the outer edge is actually moving faster in terms of raw speed. But in a galaxy, the stars at the outer edges should eventually slow down because the gravitational pull from the center grows weaker with distance. The farther out you go, the less pull there is. The less pull there is, the slower the orbit should be. This is basic physics. It is the same reason the outer planets in our solar system move more slowly than the inner ones. Neptune drifts along at just 12 miles per second. Mercury races at nearly 30. So when astronomers began measuring the rotation of galaxies in detail, they fully expected to see the same pattern. Stars near the center spinning fast. Stars near the outer edges spinning slow. A smooth, predictable curve of motion that matched the known laws of gravity. That is not what they found. The stars at the outer edges of galaxies were moving far too fast. Not slightly faster than expected. Dramatically faster. Fast enough that, by all rights, they should have been flung out into empty space long ago. If you spin a ball on a string and cut the string, the ball flies away. The outer stars of these galaxies were like that ball, except the string had not been cut. They were still there, still orbiting, still holding on. Something was keeping them in place. Something was providing the gravitational grip that the visible matter simply could not supply. This was the puzzle. The light from a galaxy only comes from its stars, its gas clouds, and its glowing dust. Astronomers could measure all of that. They could add it up. And when they did, the total mass of all that visible material was nowhere near enough to explain the speeds they were seeing. The math did not work. The galaxy should have been tearing itself apart. Instead, it was spinning along, perfectly intact, as if held together by something invisible. The first scientist to notice this pattern clearly was a Swiss astronomer named Fritz Zwicky. Back in the 1930s, Zwicky was studying not individual galaxies, but clusters of galaxies, groups of hundreds, or thousands of galaxies bound together by gravity. He measured how fast the individual galaxies within one of these clusters were moving, and he found the same problem. They were moving too fast. The visible matter in the cluster was not nearly enough to hold them together. Zwicky calculated that there had to be far more mass present than anyone could see. He called it Dunkel Materie, dark matter. His colleagues largely ignored him. Zwicky was known for bold ideas, and this one seemed too strange. There was no direct evidence for invisible mass. There was only the motion of galaxies, and motion could be tricky to measure. The idea sat quietly for decades, waiting. Meanwhile, the galaxies kept spinning. Every galaxy that astronomers turned their instruments toward showed the same stubborn, impossible rotation. The outer stars refused to slow down. The data kept piling up, and slowly, the scientific community began to take the problem seriously, not because anyone had found dark matter directly, but because the alternative was worse. The alternative was admitting that gravity itself, one of the most tested and trusted forces in all of physics, was somehow broken at the scale of galaxies. That seemed far less likely than the possibility of unseen mass. What Zwicky had glimpsed in the 1930s was not a fluke. It was a signal, a quiet, persistent signal hidden inside the motion of stars, written into the rotation curves of galaxies across the entire observable universe. Every galaxy told the same story. Every measurement confirmed the same gap between what was visible and what had to be there. The universe was holding itself together with something we could not see. And the spinning of galaxies was the first clear whisper of that truth, patient and steady, waiting for someone to finally listen. That someone was Vera Rubin. She grew up in Washington, D.C., and fell in love with the night sky as a child. She would press her face against her bedroom window and watch the stars wheel slowly overhead. That quiet wonder never left her. She went on to become one of the most careful and persistent observers in the history of astronomy. And in the 1970s, working alongside physicist Kent Ford, she did something that would reshape our understanding of the universe. Rubin and Ford pointed their telescope at the Andromeda Galaxy, our nearest large galactic neighbor, about 2.5 million light-years away. They were not looking for anything mysterious. They simply wanted to map how fast different parts of the galaxy were rotating. It was careful, methodical work. Night after night, they measured the speed of stars at different distances from the galaxy's bright center. What they expected was simple. Stars close to the center, where most of the visible mass was packed together, should move fast. Stars far out on the edges, far from that concentrated pull of gravity, should move slower. This is how our own solar system works. Mercury, the closest planet to the Sun, races around its orbit. Neptune, far out in the cold dark, moves much more slowly. The same logic should apply to galaxies. But the stars in Andromeda did not obey that logic. The outer stars moved just as fast as the inner ones. Some of them moved even faster. No matter how far from the center Rubin and Ford measured, the rotation speed stayed stubbornly, impossibly flat. The curve that should have dropped off simply did not drop. It stretched outward, level and steady, like a line drawn by a ruler. Rubin knew immediately that something was wrong, or rather, that something was missing. The visible stars and gas in Andromeda could not account for the gravity needed to hold those fast-moving outer stars in their orbits. If only the visible matter existed, those outer stars would fly off into space. The galaxy would tear itself apart, but it did not tear itself apart. It held together, calm and whole, spinning in the dark. The only explanation that made sense was invisible mass. A vast, unseen reservoir of material surrounding the galaxy, extending far beyond its glowing disk of stars. This invisible material would provide the extra gravitational pull needed to keep those outer stars locked in their orbits. Rubin called it a problem of missing mass. Today, we call it dark matter. What made Rubin's work so powerful was not just one galaxy. She and Ford went on to study dozens of galaxies, one after another, across years of careful observation. Every single galaxy showed the same flat rotation curve. Spiral galaxies, elliptical galaxies, large galaxies, small galaxies. The pattern held everywhere they looked. This was not a measurement error. This was not a quirk of one unusual system. This was a universal feature of galaxies across the cosmos. By the late 1970s and into the 1980s, Rubin had published her findings widely. The data was meticulous and thorough. Other astronomers checked her work and found the same results. The scientific community, which had been slow to accept Zwicky's earlier claims, could no longer look away. The rotation curves were too consistent, too clear, too widespread to dismiss. Rubin herself was always careful about what she claimed. She did not say she had discovered dark matter. She said she had found evidence that something unseen was shaping the motion of galaxies. She trusted the data and let it speak. That kind of quiet discipline is what made her work so lasting. There is something deeply moving about the way this discovery unfolded. Rubin was not looking for a revolution. She was doing patient, precise work, measuring the speeds of distant stars with a spectrograph. The instrument that splits light into its component colors and reveals how fast a source of light is moving toward or away from us. The universe handed her its secret not through a dramatic explosion or a sudden flash, but through a flat line on a graph, a line that refused to fall. That flat line changed everything. It told us that the bright, glowing matter we can see, the stars and gas and dust that make up the visible universe, is not the whole story. It is, in fact, only a small part of the story. The rest is dark. The rest is invisible. And it is everywhere, wrapped around every galaxy like a vast, silent shell, holding the visible universe together from the outside in. Vera Rubin listened to what the galaxies were saying. And what they said was this: the universe is far larger, far stranger, and far more full than it appears. So the question became, what is this invisible thing? Scientists had the shape of the mystery. Now they needed to understand what could possibly fill it. The first step, strangely enough, was learning what dark matter is not. And that list is long. Ruling things out is real science. It is how you close doors until only one remains open. For a while, some scientists thought dark matter might simply be ordinary matter that we could not see, not some exotic new substance, but familiar stuff. burned out stars, cold gas clouds, dim, failed stars called brown dwarfs, objects that never quite gathered enough mass to ignite. These were given a name, machos, which stands for massive astrophysical compact halo objects. It is a bit of a playful name for something scientists took very seriously. The idea made sense at first. Space is full of things we cannot see with our eyes. A cold, dark star drifting through the void would be nearly impossible to spot. If enough of these objects existed, perhaps they could account for the missing mass. Telescopes searched for them. Scientists watched distant stars for the telltale flicker that happens when a massive dark object passes in front of them and bends their light. They found some, but not nearly enough. Machos could not explain the full picture. The numbers simply did not add up. So ordinary matter, even the dark and invisible kind, was not the answer. This was a profound moment. It meant the missing mass was not made of protons and neutrons, the tiny particles that make up everything we have ever touched, every rock, every ocean, every star we have ever seen. Dark matter had to be something else entirely. Something built from particles that do not exist in the standard periodic table of elements. Something that plays by different rules. Here is one of those rules, and it is a striking one. Dark matter does not interact with light at all. It does not emit light the way a star does. It does not absorb light the way a dark cloud of gas does. It does not reflect light the way a moon or a planet does. Light simply passes through it as if dark matter were not there. This is why we cannot photograph it. This is why our most powerful telescopes, instruments that can see galaxies billions of light years away, see right through dark matter without registering a single photon. It is invisible not because it is hiding, but because it simply has no relationship with light whatsoever. And yet, gravity is different. Dark matter does respond to gravity. It has mass, and mass creates gravity, and gravity pulls. This is the one thread connecting dark matter to everything else. It is the one force through which dark matter speaks to the visible universe. Every galaxy sits inside a vast, invisible cloud of dark matter, and that cloud's gravity is what holds the galaxy together. Without it, the spinning stars that Vera Rubin measured would have flown outward into the void long ago. Dark matter also does not interact with itself in the way ordinary matter does. Two clouds of regular gas, when they collide, heat up, slow down, and compress. They push against each other. Dark matter clouds, when they pass through each other, do not do this. They glide through one another like two ghosts walking through the same wall. Scientists have observed this behavior in distant galaxy cluster collisions, and it tells us something important. Dark matter is not just invisible. It is also, in a sense, untouchable. It does not feel pressure. It does not heat up. It does not slow down from friction. This makes dark matter unlike anything in our everyday experience. We live in a world shaped by contact, by surfaces pressing against surfaces, by heat and light and resistance. Dark matter exists in a world where almost none of that applies. It moves through the universe, responding only to gravity, indifferent to everything else. What remains, then, is a substance that has mass, that clusters and clumps under its own gravity, that shapes the large-scale structure of the cosmos, and yet cannot be seen, touched, heated, or lit. It passes through planets. It passes through you, right now, in enormous quantities, without leaving any trace. Scientists believe that roughly 84% of all the matter in the universe is dark matter. The familiar matter, the kind that makes stars and planets and people, makes up only 16% of all matter. We are the rare exception. The glowing, visible universe is the minority. The dark, silent, invisible substance is the rule. And we still do not know what it is made of. So scientists have spent decades asking a simple question. If dark matter exists, what is it actually made of? Not what it does, not how it behaves, but what is it at its smallest level? Two candidates have risen to the top of that search. Their names are WIMPs and Axions, and understanding them means shrinking down to a scale almost too small to imagine. Start with WIMPs. The name stands for weakly interacting massive particles. Each word in that name matters. Weakly interacting means these particles barely respond to anything around them. They feel gravity. They make may feel something called the weak nuclear force, one of the four fundamental forces that govern how particles behave at tiny scales. But they do not feel the electromagnetic force, which is the force behind light, heat, and magnetism. That is why they are invisible. That is why they pass through walls, through planets, through you, without stopping. Massive means they have real weight. Not massive like a mountain, but massive compared to other tiny particles. A WIMP, if it exists, would likely weigh somewhere between 10 and 10,000 times the mass of a proton. A proton is the tiny particle at the center of every atom. It is almost impossibly small. About 10 million protons laid side by side would stretch across the width of a single human hair. And yet, a WIMP could be 10,000 times heavier than even that. It would be a heavyweight in the world of the very small. Here is a way to feel that scale. Imagine the entire Milky Way galaxy shrunk down to the size of a dinner plate. On that plate, our solar system would be smaller than a single atom. And on that atom, a WIMP would be smaller still. The universe operates across ranges of size that the human mind was not built to hold. We live comfortably in the middle, somewhere between the vast and the microscopic. Dark matter lives at the far end of the small. Scientists believe that if WIMPs exist, they were created in the first moments after the Big Bang, when the universe was unimaginably hot and dense. In those first seconds, particles of all kinds were being born and destroyed constantly. As the universe cooled, most of those exotic particles vanished. But WIMPs, scientists think, would have survived in just the right numbers to account for the dark matter we observe today. This idea has a name. Physicists call it the WIMP miracle, because the math works out almost perfectly without being forced to. The numbers fit. That kind of elegant agreement between theory and observation is rare, and it is one reason WIMPs remain such a compelling suspect. The second major candidate is the axion. Axions are very different from WIMPs. Where WIMPs are heavy, axions are extraordinarily light. Some estimates suggest an axion could be 1 trillion times lighter than an electron. The electron is already one of the lightest known particles. So an axion, if it exists, would be almost ghostly in its smallness. And yet, because the universe may contain them in almost unimaginable numbers, their combined mass could still account for all the dark matter we observe. Axions were not invented to explain dark matter. They were first proposed in the late 1970s to solve a completely separate problem in particle physics, a puzzle about how certain forces behave at the quantum level. Scientists noticed later that axions, almost by accident, had exactly the right properties to be dark matter. That kind of unexpected connection, where a solution to one problem quietly solves another, is one of the quiet pleasures of physics. Both WIMPs and axions are hypothetical. No one has directly detected either one yet. But the search is active and serious. Underground laboratories, shielded from cosmic radiation by miles of solid rock, run experiments that wait patiently for a single WIMP to bump into an ordinary atom. Other experiments cool metal chambers to temperatures colder than deep space, hoping to catch the faint signal of an axion converting into a photon, a particle of light. These are some of the most sensitive instruments ever built by human hands. What makes this search so striking is its patience. Scientists are hunting for a particle that barely interacts with anything, using detectors that must be almost perfectly quiet, waiting for a signal that may come once in months or years. It is slow, careful, hopeful work, and it is driven by a simple fact. 84% of all the matter in the universe is made of something we have never directly touched. Whatever that something is, it shaped every galaxy you have ever seen in a photograph. It shaped the galaxy you live in right now. And so we arrive at something remarkable. Dark matter did not just fill the universe quietly, like dust settling on a shelf. It built the universe. It drew the blueprints. Long before the first star ever burned, dark matter was already gathering, pulling, and shaping the structure of everything that would come after. Picture the universe as it looked roughly 14 billion years ago, not long after the Big Bang. Ordinary matter, the kind made of atoms, was spread almost evenly through space. It was hot and dense, and moving too fast to clump together on its own. Left alone, it might have stayed that way. A smooth, featureless fog drifting through the dark. But dark matter was already doing something different. Dark matter does not feel heat the way ordinary matter does. It does not bounce around or radiate energy. So even in those earliest moments, it could begin to slow down and gather. Tiny regions where dark matter was slightly denser than average began to pull in more dark matter from the space around them. Slowly, over millions of years, those regions grew into vast clumps. Scientists call these clumps dark matter halos, and they acted like invisible scaffolding for the universe. Ordinary matter, still cooling and slowing down, eventually fell into those halos. It followed the gravity that dark matter had already laid down. Gas collected in the deepest pockets of that invisible structure. It compressed, it heated, and eventually it ignited into stars. The galaxies you see in photographs, those spirals and ellipses glowing with billions of suns, did not form randomly. They formed where dark matter told them to. This is one of the most striking ideas in all of modern science. The visible universe, every star, every planet, every cloud of glowing gas, is arranged the way it is because of something we cannot see. Dark matter is the frame. Ordinary matter is the painting stretched across it. Now imagine floating far above the universe, high enough to see the whole thing at once. What you would see is not a random scatter of galaxies. You would see structure. Long, thin threads of galaxies stretching across enormous distances. Flat sheets where galaxies cluster together, and between them, vast empty regions called voids, where almost nothing lives at all. This pattern, this web of threads and sheets and empty spaces, is called the large-scale structure of the universe. And dark matter is what created it. The threads you would see are not small. Each one can stretch for hundreds of millions of light years. A single light year is about 6 trillion miles. These filaments, those long strands connecting galaxy clusters, contain dark matter running through them like a hidden spine. Ordinary matter clings to that spine. Galaxies form along it like beads strung on a wire you cannot see. The empty voids between those filaments are just as important. They are not accidents. Dark matter drains those regions early in the universe's history, pulled toward the denser areas. Ordinary matter followed. What was left behind was almost nothing. Some voids are hundreds of millions of light years across. They are among the largest structures in the known universe, and they are defined almost entirely by the absence of dark matter. Scientists have used powerful computer simulations to model how this all happened. They start with the conditions of the early universe and let the physics run forward in time. When they include dark matter in those simulations, the result matches what we actually observe. The filaments appear. The voids appear. The galaxy clusters appear in the right places, at roughly the right sizes. When scientists run the same simulation without dark matter, the universe comes out wrong. Smooth and featureless. No web, no structure, just a fog. That match between simulation and observation is one of the strongest pieces of evidence we have that dark matter is real. We cannot touch it. We cannot photograph it directly. But when we model the universe with it, the universe looks like the universe. When we model the universe without it, it does not. There is something quietly moving about that. The structure of everything, the reason galaxies exist in clusters and chains rather than scattered randomly. The reason the night sky looks the way it does traces back to a substance we have never held in our hands. Dark matter shaped the largest things in existence, and it did so gently, invisibly, over billions of years, simply by following the rules of gravity with a patience that no human mind can fully imagine. The web it built is still there, still growing, still pulling matter slowly toward its densest points. The universe is not finished yet. There is a trick that space plays on us, and it is one of the most beautiful tricks in all of science. Light travels in straight lines. That is something we learn early, and it feels permanent, like a rule carved into the nature of things. But gravity can bend light, not redirected clumsily, the way a mirror does, but curve it gently, smoothly, the way a lens curves the light passing through glass. When light from a distant galaxy travels across the universe toward us, it does not always arrive in a straight line. If something massive sits between that galaxy and our eyes, the gravity of that mass massive object pulls the light slightly off course. The light curves around it, and when it reaches us, the galaxy behind looks stretched or smeared or multiplied into arcs and rings of soft color. This effect is called gravitational lensing. Einstein predicted it more than a century ago. As part of his theory of general relativity, his great description of how gravity works. He understood that mass warps the space around it, and that light follows the shape of space. So wherever there is enough mass, light will bend. The first confirmation came in 1919, when astronomers watched starlight curve around the edge of our own sun during a solar eclipse. That moment made Einstein famous overnight. But the story did not end there. It kept going deeper into the dark. Here is where dark matter enters the picture in a way that is almost impossible to ignore. When astronomers map the way light bends around galaxy clusters, those massive groups of hundreds or thousands of galaxies bound together by gravity, they can calculate how much mass must be present to produce that bending. They add up all the visible matter, the stars, the gas, the dust, everything they can detect with any instrument, and the numbers do not match. The bending is far too strong. The light curves far more than all the visible matter could ever cause. Something else is there. Something with enormous mass. Something that bends light just as powerfully as ordinary matter does, but produces no light of its own. That something is dark matter. Gravitational lensing became one of the clearest windows we have ever had into the invisible. Astronomers can now use it deliberately, like a tool. They look for galaxies behind massive clusters and study how distorted those background galaxies appear. The more distorted the image, the more mass must be present in the cluster. By carefully measuring those distortions, scientists can map where the mass is concentrated, even the mass they cannot see directly. They are drawing maps of the invisible by reading the way light bends around it. Some of these lensed images are extraordinary to look at. A single distant galaxy can appear as a ring of pale blue light, thin and perfect, circling a foreground cluster like a halo. This is called an Einstein ring, and it forms when the background galaxy, the massive cluster, and our telescope line up almost exactly. The light from that distant galaxy wraps all the way around the cluster and arrives at us from every direction at once, forming that glowing circle. It is one of the rarest and most striking sights in astronomy. Other times, lensing splits a single galaxy into 2, 3, or even 4 separate images, arranged in a cross pattern. Astronomers call this an Einstein cross. Each image is the same galaxy, seen from slightly different paths around the same massive object in the foreground. The universe is using dark matter as a magnifying glass, and in doing so, it reveals its own hidden weight. What makes this so remarkable is that lensing does not care what kind of matter is doing the bending. It only cares about mass. Dark matter has mass. It curves space. It bends light. And so even though we cannot see it, cannot touch it, cannot collect a sample of it, it leaves a signature in the light that passes near it. Every arc, every ring, every smeared and stretched image of a distant galaxy carries information about the invisible mass that shaped its path. Scientists have now cataloged thousands of gravitational lenses across the sky. Each one is a kind of portrait of dark matter, drawn in bent light. The universe is full of these quiet signatures, written in the curves of ancient starlight that traveled billions of years only to arrive here, gently warped by something we still do not fully understand. The light tells us the truth, even when the thing bending it refuses to be seen. There is one place in the sky where dark matter did something it almost never does. It showed itself, not directly, not in a way you could photograph or hold, but clearly enough that scientists looked at the data and felt something shift. The place is called the bullet cluster, and what happened there changed the way we understand the invisible universe. The bullet cluster is actually 2 galaxy clusters that collided. A galaxy cluster is a vast group of hundreds or even thousands of galaxies, all bound together by gravity. These 2 clusters were moving toward each other through space for a very long time. Then, roughly 150 million years ago, they passed through one another. The collision was not like 2 cars hitting head-on. It was slower, stranger, and far more revealing. When the two clusters met, the ordinary matter inside them behaved exactly as physics said it would. The hot gas that fills galaxy clusters, a thin glowing cloud of charged particles called plasma, slammed into the opposing gas and slowed down. The two clouds of gas collided, heated up, and released a burst of X-ray light. Astronomers could see this clearly. The glowing gas piled up in the middle of the collision zone, like water pushed into a wave by two boats passing close together. But something else happened, something that the gas did not do. The galaxies themselves, and whatever dark matter surrounded them, passed right through the collision almost without slowing down at all. Galaxies are so spread out, so sparsely populated with actual stars, that two galaxy clusters can pass through each other, and the individual galaxies rarely collide. They just drift through, and the dark matter, which does not interact with ordinary matter in any strong way, passed through just as cleanly. So after the collision, the ordinary gas sat in the middle, glowing in X-rays, slowed and compressed. But the galaxies and their surrounding dark matter had moved ahead, separating from the gas on both sides. The two components had come apart. The ordinary matter was in one place. The mass was somewhere else. This is where gravitational lensing came back in. Scientists used the bending of background light to map where the actual mass was located in the bullet cluster. They were looking for the invisible weight, and what they found was striking. The mass was not where the gas was. The mass had moved ahead with the galaxies. There were two large concentrations of invisible mass, one on each side of the collision, separated from the glowing gas cloud sitting between them. The dark matter had passed through the collision like a ghost through a wall. The ordinary matter had not. This was not a small result. This was one of the most direct pieces of evidence ever gathered that dark matter is real, and that it is separate from ordinary matter. Before the bullet cluster, some scientists had proposed that maybe we did not need dark matter at all. Maybe our understanding of gravity was simply wrong at large scales, and a modified version of the laws of physics could explain the strange behavior of galaxies without any invisible substance. These ideas are called modified gravity theories, and they had serious supporters. The bullet cluster made those explanations very difficult to hold onto. If you modified gravity to explain the missing mass, the mass should still follow the gas, because the gas is where most of the ordinary matter is. But the mass did not follow the gas. The mass went with the galaxies, ahead of the gas, separated cleanly by the collision. Something real had moved through that collision and kept going. Something with mass, but without the ability to interact with the gas the way ordinary matter does. There is a rhythm to how science works. Evidence builds slowly. A hint here, a pattern there. Decades of rotation curves and gravitational lensing, each one adding a quiet note to the same song. And then something like the bullet cluster arrives, and the song becomes undeniable. The evidence does not shout. It simply accumulates, patient and steady, until the picture is too clear to look away from. The bullet cluster is now one of the most studied objects in modern astronomy. It has been observed across many wavelengths of light, from radio waves to X-rays, each observation adding more detail to the same story. Two clusters collided. The gas slowed. The dark matter did not. And in that separation, in that quiet parting of the visible from the invisible, the universe offered us something rare. A moment where the hidden structure of reality left a mark we could actually read. Every galaxy we can see sits inside something we cannot see. A vast, invisible shell of dark matter surrounds each one, extending far beyond the visible stars and gas. Scientists call these structures dark matter halos. The word halo fits well. Picture a soft glow around a lamp on a foggy night, spreading outward in every direction, much larger than the lamp itself. A dark matter halo works the same way, except there is no glow. There is only mass, silent and spread wide, holding everything inside it together. Our own Milky Way sits inside one of these halos right now. The halo around our galaxy stretches outward for hundreds of thousands of light years. A single light year is about 6 trillion miles. The visible disk of the Milky Way, the part with the stars and spiral arms we can see in photographs, is only a small fraction of the full structure. The stars are the bright center. The halo is the enormous, invisible body surrounding them. This is one of the most striking things about dark matter halos. They are not small additions to galaxies. They are the dominant structure. The dark matter halo of the Milky Way contains far more mass than all the stars, gas, and dust inside the galaxy combined. The visible parts of a galaxy, the things we can actually photograph and measure with light, make up only a small portion of the total mass. The halo holds the rest, quietly and completely. Halos are not perfectly round. Scientists who model dark matter using powerful computer simulations find that halos tend to be slightly stretched, more like an egg than a perfect sphere. They are lumpy in places, with smaller clumps of dark matter orbiting inside the larger halo. These smaller clumps are sometimes called subhalos. Some of them may contain small satellite galaxies, tiny companions orbiting the larger galaxy, like moons around a planet. The Milky Way has several of these satellite galaxies. The large and small Magellanic Clouds, two small galaxies visible from the southern hemisphere as faint smudges of light, are among the most well-known. They orbit inside our galaxy's dark matter halo. The halo does not just sit there passively. It shapes the galaxy it surrounds. The gravitational pull of the halo affects how gas falls inward to form new stars. It influences how the spiral arms of a galaxy stay organized over billions of years. Without the halo, the visible structure of a galaxy would behave very differently. The halo is not decoration. It is the framework that makes the galaxy possible. When two galaxies pass close to each other, their halos interact first. The halos are so large that they begin to overlap and pull at each other long before the visible stars come anywhere near. This gravitational conversation between halos can stretch and distort both galaxies, pulling out long streams of stars called tidal tails, the antennae galaxies, a famous pair of colliding galaxies captured in stunning detail by the Hubble Space Telescope, show exactly this kind of distortion. Two galaxies, two halos, pulling at each other across enormous distances, reshaping each other over hundreds of millions of years. Halos also grow over time. In the early universe, dark matter began clumping together under its own gravity. Smaller halos formed first, then merged into larger ones. This process, called hierarchical structure formation, means that the large halos we see today are the result of countless smaller halos combining over billions of years. Galaxies grew inside these merging halos, carried along by the larger gravitational structure around them. The visible universe we see today, with its galaxies and clusters, is in many ways a map of where the dark matter halos ended up. There is something deeply settling about this picture. Every galaxy, including our own, is not alone in space. It is nested inside a structure far larger than itself. The stars and planets and everything we can see are held gently inside this invisible shell. The way a seed sits inside a fruit, the halo came first, in a sense. The dark matter gathered, and then the ordinary matter followed, drawn inward by gravity, eventually forming the stars and worlds we know. We live inside one of these halos. Right now, as you listen to this, dark matter is passing through the room around you, through the earth beneath you, through the entire solar system. The halo of the Milky Way reaches all the way here. It has always been here. We are not separate from the invisible universe. We are inside it, held by it, shaped by it, in ways we are only beginning to understand. And that shaping began earlier than you might expect. Long before the first star ever lit up, long before any light existed at all, dark matter was already doing its quiet work. It was pulling, gathering, building the scaffolding that everything else would eventually grow on. The universe, in its earliest moments, was almost perfectly smooth. The gas and energy spread out in every direction in a near-perfect fog. But it was not perfectly smooth. There were tiny differences, tiny patches where the density was just slightly higher than everywhere else. These differences were so small that if you could have seen them, they would have looked like the faintest ripples on a still pond. And yet those ripples changed everything. Dark matter felt those ripples first. Because dark matter does not interact with light the way ordinary matter does, it was free to move and clump together even in that early, blazing hot universe. Ordinary matter was stuck It was tangled up with radiation, pushed and pulled by the intense heat and light of the young cosmos. It could not collapse into clumps yet, but dark matter could, and it did. This is one of the most extreme facts about dark matter. It started building structure in the universe hundreds of millions of years before ordinary matter was even free to move on its own. Dark matter had a head start. It gathered into clumps and halos, while the rest of the universe was still a glowing, churning sea of particles and light. Then, around 380,000 years after the Big Bang, something changed. The universe cooled enough that electrons and protons could finally join together to form hydrogen atoms. Physicists call this moment recombination, the point when matter and light finally separated from each other. The fog lifted. The universe became transparent for the first time, and ordinary matter, now free from the grip of radiation, could finally begin to fall. It fell into the dark matter halos that had been waiting for it. The hydrogen gas, the most common element in the early universe, drifted inward along the invisible gravitational wells that dark matter had already carved out. It flowed like water, finding the lowest point in a landscape. The dark matter halos acted like bowls, and the gas poured in. As the gas fell deeper and deeper, it compressed. It grew denser. It grew hotter. And eventually, in the very center of these dark matter structures, the pressure and heat became so extreme that hydrogen atoms began to fuse together. The first stars were born. These first stars were almost nothing like the stars we see today. Scientists believe they were enormous, far larger than our sun. Some estimates suggest they could have been hundreds of times more massive than our sun, burning with an intensity we have never directly observed. They are sometimes called population III stars, a name astronomers use for this first generation of stars that formed from pure hydrogen and helium, with no heavier elements at all. No carbon, no oxygen, no iron, just the lightest elements forged in the Big Bang, now burning inside the gravitational cradles that dark matter had built. These stars burned fast and hot and died young. A star that massive cannot last long. It burns through its fuel in perhaps 1,000,000 years, which in cosmic time is barely a breath. When they died, they exploded as supernovae, scattering the first heavier elements into the universe. Carbon, oxygen, silicon, iron, the raw materials of planets, the raw materials of life, all of it seeded into space by these first enormous stars born inside dark matter halos. Without the halos, the gas would not have gathered. Without the gathering, the pressure would not have built. Without the pressure, no fusion, no first stars, no heavy elements scattered into space, no rocky planets, no oceans, no anything. The chain runs all the way back to those tiny ripples in the early universe, those faint differences in density that dark matter responded to first. It is one of the longest chains of cause and effect in all of science. A slight unevenness in the infant cosmos, detected by something invisible, amplified over millions of years, eventually producing the stars that made the atoms in your body. The extremes here are staggering. The first stars may have been hundreds of times more massive than our sun. The dark matter halos that cradled them formed when the universe was less than 100 million years old, and the whole process, from that first faint ripple to a burning star, took less time than it took for complex life to appear on Earth. Dark matter did not just shape the universe we see, it helped ignite it. And so the universe did not stop there. The ignition of those first stars was only a beginning. What followed was something even more vast, even more strange, and even more beautiful in its quiet complexity. Picture the universe as it looks today, if you could step far enough back to see the whole of it at once. Not the neat, scattered points of light we imagine when we close our eyes and think of space. Something far more structured, far more deliberate. Across billions of light years, galaxies do not float alone. They gather, they cluster, they string themselves along enormous threads, like drops of water clinging to a spider's web after rain. Scientists call this the cosmic web, and it is one of the largest structures that exists anywhere in the known universe. Those threads have a name. Astronomers call them filaments. Each filament is a long, thin bridge of gas and dark matter, stretching across tens of millions of light years. Galaxies form along these filaments the way towns form along rivers. The filaments carry material. They carry gas. And they carry the invisible dark matter that first drew everything together. Without the filaments, galaxies would not cluster the way they do. Without the clusters, the universe would look nothing like what we observe. Here is the quiet detail that scientists find so striking. The cosmic web was not built by ordinary matter. It was built by dark matter first. Long before stars existed, dark matter had already begun pulling itself into these long, thread-like shapes. The ordinary gas and dust followed later, falling into the structure that dark matter had already made. The web was the scaffolding. Everything we can see was built on top of it. The filaments are not the only feature. Between them lie enormous empty spaces. Scientists call these voids. A void is a region of space where almost nothing exists. No galaxies, very little gas, very little dark matter. Some voids are hundreds of millions of light years across. They are among the emptiest places in the known universe, and they sit between the filaments like bubbles between the threads of that great web. The universe, at its largest scale, looks something like a sponge. Dense walls and threads surrounding vast, hollow spaces. One of the most remarkable things about the cosmic web is how well scientists predicted it before they could fully see it. Computer simulations, using what we know about dark matter and gravity, produced webs that look almost identical to what telescopes actually observe. The simulations and the real universe match. That agreement is one of the strongest pieces of evidence we have that our understanding of dark matter, even without knowing exactly what it is, captures something deeply true about how the universe works. The filaments also carry something else. Between galaxies, threading through the web, there is warm gas that scientists call the warm-hot intergalactic medium. This gas sits at temperatures between 100,000 and 10 million degrees. For a long time, scientists could account for only about half the ordinary matter the universe should contain. The rest seemed to be missing. Evidence now suggests that much of this missing matter hides inside the filaments. In this warm, diffuse gas that is very hard to detect, cosmic web may be holding a significant portion of all the ordinary matter in the universe, spread thin across those vast threads. Zoom in closer, and the details become even finer. Where filaments meet, matter concentrates most heavily. These meeting points are called nodes, and they are where the largest galaxy clusters tend to form. The biggest structures in the universe, clusters containing hundreds or even thousands of galaxies, sit at these intersections. They are the knots in the web, and at the center of many of these clusters, enormous black holes sit quietly, fed by the material that the filaments funnel inward over billions of years. There is something deeply calming about this picture once you sit with it. The universe is not random. It is not chaos. It has shape. It has pattern. The same dark matter that responded to tiny ripples in the infant cosmos eventually produced this enormous, intricate structure, stretching across the observable universe in every direction. A structure so large that our entire galaxy, with its hundreds of billions of stars, is just one small bead on one small thread. The cosmic web is the quiet architecture of everything. Most of it is invisible. Most of it is dark matter and empty space. And yet, it holds the whole visible universe in place, the way bones hold a body together, unseen beneath the surface, doing their work in silence. So scientists knew the cosmic web was there. They could see its effects in the way galaxies clustered and moved. They could trace its outline through gravitational lensing. But knowing something exists and actually detecting it are very different things. For decades, physicists have been trying to catch dark matter in the act, to find a single particle, just one, and hold up the evidence and say, here it is. That search has taken them somewhere unexpected, not up into the sky, down into the earth. The logic is elegant in its simplicity. Space is full of noise. Cosmic rays, the fast-moving particles that stream in from distant supernovae and other violent events, constantly bombard the surface of our planet. Ordinary radiation from rocks and soil adds to that background hum. If you want to detect something as rare and shy as a dark matter particle, you cannot do it at the surface. All that noise would drown out any signal before you could find it. So physicists went underground, sometimes very far underground, to find the quiet they needed. One of the most famous of these experiments sits nearly a mile beneath the Black Hills of South Dakota, inside a former gold mine called the Homestake Mine. The mine itself has a long history in science. In the 1960s, a physicist named Raymond Davis Jr. used it to detect neutrinos, the ghostly particles produced by the sun. He lowered a tank of cleaning fluid deep into the rock and waited for neutrinos to pass through it. Most passed through without leaving a trace, but a few interacted, and Davis counted them. He won the Nobel Prize for that work. The same mine, now called the Sanford Underground Research Facility, is home to some of the most sensitive dark matter detectors ever built. The detectors themselves are extraordinary objects. One experiment, called LuxC-PLIN, or LZ, uses a tank filled with about 10 tons of liquid xenon, a heavy, clear element that glows faintly when a particle passes through it. The tank is surrounded by layers of shielding, water tanks, and other materials designed to block out every possible source of background radiation. Scientists cool the xenon to extremely low temperatures and then wait. If a dark matter particle, specifically a WIMP, the leading candidate physicists have long suspected, passes through the xenon and collides with a xenon atom, it should produce a tiny flash of light. That flash would be the signal. That flash would be the proof. The patience required for this kind of science is hard to describe. Researchers run these experiments for months and years at a time. They analyze every flicker of light the detector records, trying to separate the rare, genuine signals from the constant background of ordinary particles that slip through despite all the shielding. So far, no confirmed detection of a dark matter particle has been made. The detectors have grown more sensitive with each generation. The searches have gone deeper and longer, and still, dark matter has not shown itself directly. This is not failure. This is science doing exactly what it is supposed to do. Each null result, each experiment that finds nothing, tells physicists something important. It rules out certain masses and interaction strengths for WIMPs. it narrows the search. The universe is not making this easy, but the universe rarely does. Other experiments take different approaches. Some look for axions, the lighter, quieter candidates, using powerful magnetic fields and sensitive microwave detectors. The ADMX experiment, based in the United States, works by trying to coax axions into converting into detectable photons, tiny packets of light, inside a strong magnetic field. It is a delicate and painstaking process, scanning through possible axion masses one thin slice at a time. Other detectors have been built in tunnels beneath the Alps, in mines in Italy and Canada and China, each one a quiet outpost in this global search. There is something moving about this picture. Thousands of scientists spread across the world, sitting in the deep dark beneath mountains and plains, surrounded by rock and silence, waiting for a whisper from the invisible universe. They have built the most sensitive instruments in human history. They have gone to extraordinary lengths to remove every source of noise, every distraction, just to listen more clearly. And they are still listening. The dark matter that built the cosmic web, that shaped every galaxy, that guided the formation of the first stars, passes through these detectors constantly. It passes through the earth. It passes through you. It has been here all along, woven through everything, patient and silent, while we build better and better ears, hoping one day to finally hear it speak. While those detectors waited in silence beneath the earth, something else was happening above ground. Something that would shake the entire field of cosmology to its core. In 1998, two separate teams of astronomers set out to do something that seemed almost routine. They wanted to measure how fast the universe was slowing down. That last word is important. Slowing down. Every scientist in the world assumed the universe was decelerating. After all, the Big Bang had sent everything flying outward in a great, expanding rush. And gravity, the great pulling force, should have been tugging all of that matter back together. Maybe not enough to reverse the expansion entirely, but enough to put the brakes on. The universe should have been coasting, gradually losing speed, the way a ball thrown into the air loses speed as it rises. Everyone agreed on this, It was not even a question worth debating. The two teams used a special kind of exploding star called a type Ia supernova. These explosions are remarkable tools for astronomers. Every single one of them releases almost exactly the same amount of light. That makes them useful as cosmic measuring sticks. If you know how bright something truly is, and you can see how dim it appears from Earth, you can calculate exactly how far away it is. The teams used these supernovae to map the expansion of the universe across billions of years of history. What they found stopped them cold. The distant supernovae were dimmer than they should have been. Not slightly dimmer, measurably, undeniably dimmer. And dimmer meant farther away. And farther away meant the universe had not been slowing down at all. It had been speeding up. The expansion of the universe was accelerating. Something was pushing space itself outward, faster and faster, and no one had any idea what it was. The two teams checked their data. They checked it again. They looked for errors in their instruments, mistakes in their calculations, any possible explanation that did not require rewriting the laws of physics. There were none. Both teams, working independently, arrived at the same impossible answer. The universe is not coasting. It is racing. This discovery won the Nobel Prize in Physics in 2011. The scientists who led those teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, had set out to confirm something ordinary, and instead found something that overturned nearly everything. It is one of the most dramatic reversals in the history of science. The force driving this acceleration was given a name: dark energy. It is not dark in the way a shadow is dark, not an absence of light in any simple sense. It is dark because we cannot see it, cannot measure it directly, cannot touch it or trap it or test it in a laboratory. We know it exists only because of what it does. It pushes, it stretches, it drives the universe apart at an ever-growing pace. Here is where the strangeness deepens. Dark energy does not behave like anything else we know. Ordinary matter and energy become more diluted as space expands. Pour the same amount of water into a larger and larger container, and the water gets thinner, more spread out. But dark energy does not thin out. As space appears to stay constant, or perhaps even grow. The more space there is, the more dark energy there seems to be. This is unlike anything in our experience of the physical world. Scientists call this property a negative pressure. It sounds like a contradiction. Pressure usually pushes inward, compresses, squeezes. Negative pressure does the opposite. It pulls space apart from the inside. It is as if the vacuum of space itself has a kind of tension, a built-in tendency to stretch, and the larger the universe becomes, the stronger that stretching grows. Right now, as you rest and breathe quietly, the universe is larger than it was 1 second ago. It is larger than it was when you began listening tonight. Every galaxy beyond our local group is moving away from us, carried outward on the swelling fabric of space. The galaxies are not moving through space the way a ship moves through water. Space itself is growing between them, like dots drawn on a balloon that is slowly being inflated. And dark energy is the breath inside that balloon, invisible and relentless, pushing outward without pause. We did not expect this. No one did. And that unexpected truth, found by 2 quiet teams of astronomers pointing telescopes at dying stars, changed our picture of the universe forever. The cosmos turned out to be stranger, and in its own way more astonishing than anyone had dared to imagine. Dark energy is not dark matter. That distinction matters more than it might seem at first. Dark matter is a kind of substance, something with mass, something that pulls. Dark energy is something else entirely. It is a property of space itself. It does not clump. It does not gather. It does not form halos around galaxies or help stars ignite. It is spread perfectly, evenly, through every corner of the universe, the same in every direction, the same in every void. Where dark matter behaves like a hidden ingredient in a recipe, dark energy behaves like a rule written into the recipe itself. Think of it this way. Dark matter is a thing. Dark energy is a condition. Dark matter can be mapped, at least indirectly, through the way it bends light and tugs on galaxies. Dark energy cannot be mapped the same way. It leaves no shadow. It bends no light. It simply causes space to expand faster and faster. And we see its effects only by watching how the universe grows over time. Scientists describe dark energy as a property of the vacuum. The vacuum, that word we use for the emptiness of space, is not truly empty. Quantum physics, the science of the very small, tells us that empty space is alive with tiny fluctuations, particles flickering in and out of existence in fractions of a second. This restless energy of the vacuum may be connected to dark energy, though the exact relationship is one of the deepest unsolved problems in all of science. The numbers do not quite match. The vacuum energy that quantum physics predicts is vastly larger than the dark energy we actually measure. That gap, that mismatch between prediction and observation, keeps physicists awake at night in a way that has nothing to do with sleepiness. What dark energy is not, also, is a force in the way gravity is a force. Gravity reaches out from a mass and pulls other masses toward it. Dark energy does not reach out from anywhere. It does not have a source you could point to on a map. It is simply present, everywhere at once, woven into the fabric of space at a constant density. As space expands and new space is created, more dark energy comes with it. The total amount of dark energy in the universe grows as the universe grows. This is unlike anything else we know. Matter gets diluted as the universe expands, spread thinner and thinner across a larger and larger volume. Dark energy does not dilute. It keeps its strength. This is why dark energy wins in the long run. In the early universe, matter and dark matter dominated. Gravity was the loudest voice. It pulled gas clouds together. It built galaxies. It shaped the great web of filaments and voids that stretches across the cosmos. But as the universe expanded, matter spread out and its grip weakened. Dark energy, holding steady, slowly took over. Scientists believe this shift happened roughly 5 billion years ago, around the time our own solar system was beginning to form from a cloud of ancient gas and dust. The sun was being born just as dark energy began to win its quiet contest with gravity. That connection is worth sitting with for a moment. The same era that gave us our sun, our earth, our oceans and mountains, and the air we breathe tonight, was also the era when the expansion of the universe began to accelerate. These two things are not directly linked by cause and effect, but they are part of the same chapter in cosmic history, written at the same time, in the same universe, under the same physical laws. Dark energy also connects to the large-scale structure of the cosmos in a quieter way. The great cosmic web, those long filaments of galaxies and dark matter stretching across hundreds of millions of light years, was built during the era when gravity still dominated. Dark energy did not build that web, but dark energy is now slowly pulling it apart, stretching the distances between clusters, making it harder for new large structures to form. The universe is, in a sense, finished building its grandest architecture. What exists now is what will exist, slowly spreading apart, growing quieter, and more spread out as the ages pass. Everything connects. The vacuum of space feeds the expansion. The expansion shapes the fate of galaxies. The fate of galaxies determines the long future of all the matter inside them, including the ordinary matter, the atoms, the stars, the worlds. Dark energy is not separate from this story. It is the quiet, steady current running beneath all of it, setting the pace, holding the tempo, carrying the universe forward into its long and unknown future. Albert Einstein changed how we think about space and time. He gave us equations that described the shape of the universe itself. But even Einstein, one of the greatest minds who ever lived, made a choice he later called his biggest mistake. It happened in 1917. Einstein had just finished his general theory of relativity, his grand set of equations describing how gravity works across the whole of space. When he applied those equations to the universe, something troubled him. The math kept suggesting the universe should be moving. It should be either expanding outward or collapsing inward under its own gravity. But Einstein, like almost everyone at the time, believed the universe was static. He believed it was fixed, eternal, unchanging. So he added something to his equations to hold it still. He called it the cosmological constant. Think of it as a kind of invisible pressure built into the fabric of space itself. A gentle outward push that would balance the inward pull of gravity and keep the universe from moving. It was not based on any observation. It was not suggested by any experiment. Einstein simply needed the universe to stay still, so he added a number to make it so. For about a decade, the cosmological constant sat quietly inside his equations, doing its job, holding the imaginary static universe in place. Then everything changed. In the late 1920s, an astronomer named Edwin Hubble made one of the most important observations in the history of science. He found that distant galaxies were moving away from us. Not just a few of them, all of them. And the farther away a galaxy was, the faster it was moving. The universe was not static at all. It was expanding. It had always been expanding. Einstein's equations had told him this from the start, and he had not listened. Einstein removed the cosmological constant from his equations. He called it a blunder. He felt he had let his assumptions override what the math was clearly trying to tell him. The constant was abandoned, set aside, treated as an embarrassing detour in the history of physics. And there it sat, forgotten, for most of the 20th century. Then came 1998. Two separate teams of astronomers were studying a special kind of exploding star called a type Ia supernova. These explosions are useful to scientists because they always burn at roughly the same brightness. That makes them reliable measuring tools across vast distances. The teams expected to find that the expansion of the universe was slowing down. Gravity, they reasoned, should be pulling everything back, putting the brakes on the outward rush of galaxies. What they found instead stopped them cold. The expansion was not slowing down. It was speeding up. Something was pushing the universe apart, and that push was growing stronger over time. Scientists reached back into history and found Einstein's discarded idea waiting for them, the cosmological constant, that quiet outward pressure Einstein had invented and then thrown away, suddenly looked less like a mistake and more like a clue. The math fit. A constant energy built into the fabric of space itself could explain the accelerating expansion. It matched the observations almost perfectly. Einstein had been wrong about why he added it. He added it to create a static universe, and that was indeed an error. But the idea of a constant energy woven into space, a kind of baseline pressure that never fades and never changes, turned out to describe something real, something we now call dark energy. Scientists today often use the symbol for the cosmological constant, the Greek letter lambda, as a shorthand for dark energy in their equations. It appears in the standard model of cosmology, the best current description of how the universe works on the largest scales. The model is sometimes called lambda CDM, where the lambda stands for the cosmological constant, and CDM stands for cold, dark matter. What is remarkable is how patient this idea was. It sat unused for 70 years. The universe kept expanding, kept accelerating, kept doing exactly what it was doing long before anyone had words for it. And when the observations finally caught up, the old equation was there, waiting quietly, ready to be useful again. This is how science often moves, not in straight lines, but in long, slow arcs. An idea appears too early, gets set aside, and then returns when the world is ready to understand it. Einstein's greatest mistake turned out to be one of the most important ideas in modern physics, not because he was right about everything, but because the universe itself was stranger and richer than even he had imagined. The constant he added to hold the universe still is now the best description we have of the force pulling it apart. Light is one of the oldest messengers in the universe. It travels across billions of years to reach us, and when it arrives, it carries stories written into its very color, its brightness, its shape. When we look at distant galaxies through powerful telescopes, we are not just seeing light. We are reading a record of how space itself has changed. Here is something worth sitting with quietly. The light from a very distant galaxy left its source billions of years ago. When that light began its trip, space was smaller. The universe was younger. But as that light traveled toward us, space kept stretching. Dark energy kept pushing the fabric of the universe outward in every direction, and the light stretched with it. This stretching does something visible. It shifts the color of the light. Light that starts out as blue or white gets pulled toward the red end of the color spectrum as it travels across expanding space. Scientists call this redshift. The farther away a galaxy is, the more its light has been stretched, and the redder it appears when it finally reaches our telescopes. It is like watching a sound wave get pulled apart until the pitch drops low and slow. Except here, it is light. And the thing doing the pulling is the expansion of space itself, driven by dark energy. Edwin Hubble noticed this redshift in the 1920s. He saw that distant galaxies were moving away from us, and that the farther they were, the faster they seemed to recede. This was the first real evidence that the universe was expanding at all. But what Hubble could not know then was that the expansion was not just steady. It was speeding up. Dark energy was pushing harder as time went on, stretching space at a faster and faster rate. When astronomers in 1998 measured the light from distant supernovae, those brilliant stellar explosions that burn with the light of billions of suns, they found something the redshift told them clearly. Those supernovae were farther away than they should have been. Space had stretched more than expected. The expansion was accelerating. The light had carried that message across billions of light years, and when scientists finally decoded it, the universe revealed one of its deepest secrets. Think about what that means for the light we see tonight. Every photon, every tiny particle of light that reaches your eye from a distant galaxy has been on a voyage through stretching space. It has been gently pulled and elongated by dark energy the entire way. The color you see is not the color that left the source. It is a color transformed by the expansion of the universe itself. The sky is full of these shifted, stretched messengers, and most of us never know it. There is something almost tender about this. The universe is not just expanding in some cold, mechanical way. It is leaving its signature written in light. Every galaxy we observe is slightly redder than it would be if space were still. The farther out we look, the deeper the red. At the very edge of what our telescopes can reach, galaxies glow in wavelengths of infrared light. Light that has been stretched so far it has moved beyond what human eyes can even detect. We need special instruments to read those messages, but they are there. Dark energy does not glow. It does not shine. It gives off no light of its own. And yet it shapes every beam of light that crosses the universe. It determines how far that light travels, how much it stretches, how red it becomes. In this way, dark energy is present in every image ever taken by the Hubble Space Telescope, the James Webb Space Telescope, every observatory on every mountaintop on Earth. It is the invisible hand that has shaped the canvas on which all visible light is painted. The James Webb Space Telescope, launched in late 2021, can now see galaxies so distant that their light has been traveling for more than 13 billion years. The images it sends back are full of tiny smears of red and orange light, each one a galaxy older than almost anything we can imagine. The redshift in those images is enormous. Space has stretched enormously since that light began its trip. Dark energy has been at work the entire time, quietly and steadily pulling the universe apart, one small increment at a time, across all those billions of years. Light tells us what nothing else can. It tells us how far space has stretched. It tells us how long dark energy has been working, and in its slow drift toward red, it whispers something true about the nature of the universe. Everything is moving. Everything is changing. And the light is patient enough to carry the proof all the way to us. That slow drift toward red carries a message. And the message, when you sit with it long enough, is both enormous and strangely peaceful. The universe is not standing still. It is not holding its breath. It is moving outward, always outward, and dark energy is the quiet force behind every inch of that motion. Scientists have followed this motion forward in time, running the numbers as far as they can go. And what they find on the other side is something called the Big Freeze. The Big Freeze is the name scientists give to the most likely fate of the universe. It is not a dramatic end. There is no explosion, no collapse, no sudden darkness. It is something slower and, in its own way, more profound. As dark energy continues to push space outward, galaxies will drift farther and farther apart. The distances between them will grow so vast that light from one galaxy will never reach another. Each island of stars will become truly alone, surrounded by an ocean of empty space too wide to cross. This will not happen soon. The timescales involved are almost impossible to hold in the mind. We are talking about trillions of years. The current age of the universe is about 13.8 billion years. The Big Freeze plays out over timescales thousands of times longer than that, quadrillions of years. Numbers that have no real meaning in human experience. But the physics points there, and so we follow. Inside those distant galaxies, stars will slowly burn through their fuel. The most massive stars go first, burning bright and fast, and then collapsing or exploding in brilliant supernovae. Smaller stars, like red dwarfs, burn so slowly that some of them will last for trillions of years. But even they will run out, one by one, across unimaginable stretches of time. The stars will go dark. The universe will grow quieter and dimmer, galaxy by galaxy, star by star. What remains after the stars are gone is strain and still. Black holes will persist for an extraordinarily long time. They are among the most durable objects the universe produces. But even black holes are not permanent. Stephen Hawking showed mathematically that black holes slowly lose energy through a process now called Hawking radiation, where tiny amounts of energy leak away from the edges of the black hole over time. Given long enough, even the largest black hole will evaporate completely, releasing one final faint glow of energy before vanishing. The universe will then be left with almost nothing. Loose particles, cold photons, a vast, dark, nearly silent expanse. This is the Big Freeze, not a bang, not a crunch, a long, slow exhale. And yet, even in imagining this ending, there is something worth noticing. The universe has spent billions of years building complexity. Hydrogen became stars. Stars forged heavier elements. Those elements drifted into clouds and became new stars, planets, oceans, living things. All of that building, all of that layering of structure upon structure happened because conditions were exactly right. Dark matter provided the scaffolding. Ordinary matter filled it in. Dark energy held the whole expansion at just the right pace for long enough that complexity could arise. Some scientists study the faint signals that might echo through this long future. Even now, Instruments on Earth can detect vibrations from the universe and convert them into sound. The cosmic microwave background radiation, the faint afterglow of the Big Bang, carries a kind of acoustic signal, a record of pressure waves that moved through the early universe like sound moving through a dense fluid. Scientists have converted these signals into audio, and what you hear is a deep, low hum, a rumble far below what human ears can normally detect, stretched and shifted into our range. It is the oldest sound in the universe. It is the voice of the infant cosmos, still reaching us. That hum carries information about the early universe, about how matter was distributed, about the seeds that grew into the galaxies we see today. It also carries information about dark energy, because the way those early pressure waves spread through space left patterns, that dark energy has since stretched and shifted. The sound of the beginning helps us understand the shape of the ending. There is something quietly moving about that. The first moments of the universe left a vibration in space. That vibration traveled for 13 billion years. We built instruments sensitive enough to hear it, and in its low, ancient hum, we can read the fate of everything. The universe speaks in frequencies we can barely detect, but we are listening, and slowly, carefully, we are beginning to understand what it is saying. What we hear in that ancient hum is not just sound. It is mathematics. The universe runs on numbers, and those numbers are precise in a way that is almost hard to believe. Consider this. Scientists can measure how fast the universe is expanding. That rate has a name, the Hubble constant, named after Edwin Hubble, the astronomer who first showed us that galaxies are moving away from us. The current best estimate puts that expansion rate at roughly 67 to 73 kilometers per second for every megaparsec of distance. A megaparsec is about 3.26 million light years. That means a galaxy sitting 3.26 million light years away is moving away from us at around 70 kilometers every single second. A galaxy twice as far moves away twice as fast. The math is clean. The relationship is almost perfectly proportional. And yet, dark energy complicates this in a beautiful way. If the universe were expanding at a steady rate, the Hubble constant would be just that, constant. But dark energy is not holding still. It is pushing. And because it pushes with the same strength everywhere in space at all times, its effect grows as the universe grows. More space means more dark energy. More dark energy means faster expansion. The universe is not just expanding. It is accelerating. Scientists measure this acceleration using a unit called the cosmological constant, often written as the Greek letter lambda. Einstein introduced lambda into his equations in 1917 as a way to keep the universe from collapsing under its own gravity. He later called it his greatest mistake because he thought the universe was static, and it turned out not to be. But when astronomers discovered the accelerating expansion in 1998, lambda came back. It fit the data almost perfectly. Einstein's discarded idea turned out to describe something real. The math he invented to solve one problem quietly solved a different one, decades after his death. The value of lambda is extraordinarily small. Written out, it is approximately 1.1 times 10 to the negative 52 power per meter squared. That is a decimal point followed by 51 zeros, and then a 1. It is almost nothing. And yet, that almost nothing, spread across the vast emptiness of space, adds up to a force powerful enough to push the entire universe apart at an ever-increasing speed. Small numbers, applied everywhere, become enormous forces. That is one of the quiet lessons of cosmology. Here is another number worth sitting with. Dark energy makes up roughly 68% of everything in the universe. Dark matter makes up about 27%. Ordinary matter, everything you can see and touch and measure, accounts for just under 5%. These three numbers add up to 100%, almost exactly. Scientists call this a flat universe, meaning space is not curved like the surface of a sphere or bent inward like a saddle. It is geometrically flat, and the fact that these three components add up so precisely to produce that flatness is not an accident. It is a constraint. The universe is balanced to a degree that is almost unsettling. Physicists use an equation called the Friedmann equation, developed by the Russian mathematician Alexander Friedmann in 1922, to describe how the universe expands over time. It takes into account the density of matter, the density of dark energy, and the geometry of space. When you plug in the measured values, the equation describes the universe we actually observe with remarkable accuracy. The math written on paper a century ago matches the sky we see tonight. That is what good mathematics does. It does not just describe the past. It predicts the future. And the future the Friedmann equation describes is one of endless, accelerating expansion. Galaxies will drift apart. The cosmic web will thin. The universe will grow colder and emptier with each passing billion years. But the numbers that describe this fate are not grim. They are elegant. They follow rules. They can be written down, checked, and confirmed. The universe is not random. It is governed by relationships that hold from the smallest particle to the largest structure in existence. There is something deeply calming about that. The cosmos is vast beyond imagining. It is mostly dark, mostly empty, mostly composed of things we cannot see. And yet it obeys laws. Simple, elegant, beautiful laws. The same gravity that holds you to the ground also governs the motion of galaxies billions of light years away. The same equations that describe the early universe also describe its final fate. Everything connects. Everything follows the same quiet rules. The universe is enormous, but it is not chaotic. It is ordered, and its order is written in numbers so precise, so consistent, so enduring, that they feel less like equations and more like a kind of language. The language the universe uses to describe itself. That language, it turns out, describes something almost impossibly precise. The universe we live in exists because two enormous forces reached a kind of balance. Dark matter pulls inward. Dark energy pushes outward. And the ratio between them is so exact, so finely tuned, that even a small change in either direction would have produced a universe nothing like our own. Think about what dark matter does. It gathers. It clumps. It pulls hydrogen and helium together into clouds. And those clouds collapse into stars. And those stars burn and die. scatter the elements that eventually build planets. Without dark matter, the early universe would have stayed smooth and thin. Gravity alone, working only on ordinary matter, would not have been strong enough to pull the first galaxies together in time. The universe would have expanded too fast. The gas would have spread too thin. Stars might never have formed at all. Dark energy works in the opposite direction. It pushes space apart. It drives galaxies away from each other at speeds that grow faster with every passing moment. If dark energy were even slightly stronger than it is, that expansion would have happened too quickly in the early universe. Matter would never have had time to gather. Gravity would have lost the race before it even began. The cosmos would be a cold, empty place, filled with nothing but thinning gas and fading light. Scientists call this kind of precise condition a fine-tuning problem. The numbers that describe dark matter and dark energy have to fall within an extraordinarily narrow range for a universe like ours to exist. The density of dark energy, which physicists call the cosmological constant, is about 10 to the power of 120 times smaller than the value that quantum physics alone would predict. That is not a small difference. That is a difference so enormous it is almost impossible to express in ordinary language. And yet, the actual value is exactly what it needs to be for galaxies, stars, and planets to form. This is not a coincidence scientists take lightly. It is one of the deepest unsolved puzzles in all of physics. Why is the cosmological constant so small? Why is it not zero? Why is it precisely the value that allows structure to exist? No one knows, but the fact that it is what it is, and that we are here to notice, is one of the most striking things about the universe we inhabit. Closer to home, the same kind of fragile balance shows up everywhere. Earth sits at just the right distance from the sun. A little closer, and the oceans would boil. A little farther, and they would freeze solid. The atmosphere is thin enough to let sunlight through, and thick enough to hold warmth in. It is about 60 miles deep, which sounds like a lot until you realize that if you shrank Earth down to the size of an apple, the atmosphere would be thinner than the apple's skin. That thin layer of air is what stands between life and the cold cold vacuum of space. It filters out harmful radiation from the sun. It carries water from the oceans to the mountains and back again. It holds the heat that keeps the surface warm through the night. And it is held in place by gravity, which is itself shaped by the mass of the planet, which formed from material that dark matter helped gather billions of years ago. Every layer connects to every other layer. The moon plays a role too. Its gravity steadies Earth's tilt. Without the moon, that tilt would wobble wildly over thousands of years, swinging Earth between extreme climates that might make complex life impossible. The moon formed from a collision between early Earth and a Mars-sized object, an event so violent it melted the surface of the planet. And yet, from that violence came the stable, steady world where seasons change gently and oceans stay liquid. Scientists sometimes call this the Goldilocks condition. Not too hot, not too cold, not too much dark energy, not too little dark matter. Everything in the right amount, in the right place, at the right time. The universe did not have to be this way. The laws of physics allow for many other kinds of universes. But this is the one that exists. This is the one that made stars, that made carbon, that made water, that made the ground beneath your feet and the air in your lungs. There is something very quiet and very powerful in that. The cosmos stretched across billions of light years, mostly dark, mostly empty, mostly invisible, and yet within it, on one small world, the balance held just long enough for something remarkable to appear. Life, curiosity, the ability to look up at the night sky and wonder what is out there. There is a faint glow that fills the entire sky. You cannot see it with your eyes, but it is there in every direction, at every moment. Scientists call it the cosmic microwave background, and it is one of the most important things ever discovered. This glow is the oldest light in the universe. It was released about 380,000 years after the Big Bang, when the cosmos finally cooled enough for atoms to form. Before that moment, the universe was so hot and so dense that light could not travel freely. It was trapped, bouncing around in a thick fog of energy and matter. Then, as things cooled, the fog lifted. light streamed outward in every direction. That light is still traveling today, nearly 14 billion years later, and we can detect it. When scientists map this ancient glow, they find something remarkable. It is not perfectly smooth. There are tiny ripples in it, small patches that are ever so slightly warmer or cooler than the areas around them. These ripples are not random. They are the fingerprints of the early universe, the faint echoes of how matter was arranged just moments after everything began. Those ripples tell us how much dark matter existed in the early universe. The pattern of warm and cool patches only makes sense if a large amount of invisible matter was already there, shaping how things clumped together. Without dark matter, the ripples would look different. The fact that they match our predictions so closely is one of the strongest pieces of evidence we have that dark matter is real. The cosmic microwave background also tells us something about dark energy. The way the ripples are spaced, the precise distances between them, gives scientists a way to measure the geometry of the universe. And what they find is that the universe is flat. Not flat like a table, but flat in a mathematical sense, meaning that space does not curve back on itself. For the universe to be flat in exactly this way, the total amount of energy in the cosmos, including dark matter and dark energy, must add up to a very specific number. And it does. That match is one of the most precise confirmations in all of science. But here is where the open questions begin. Even with all of this, scientists still do not know what dark matter actually is. The cosmic microwave background tells us how much of it exists. It tells us how it behaves, but it does not tell us what it is made of. No particle has ever been directly detected. No experiment has ever caught a single piece of dark matter in a detector. The leading candidates, particles called WIMPs and Axions, remain unconfirmed. They are still theoretical, still waiting to be found. Dark energy is even more mysterious. The cosmic microwave background confirms that it exists, and that it makes up roughly 68% of everything in the universe. But the background light cannot tell us why dark energy has the strength it does. Physicists can calculate what dark energy should be based on quantum theory. The science of very small things, and the number they get is wildly different from the number they actually observe. Some estimates suggest the prediction is off by a factor of 10 followed by 120 zeros. That is not a small error. That is one of the biggest mismatches in the history of science, and no one fully understands why. There is also a newer puzzle. Different teams of scientists, using different methods, have measured how fast the universe is expanding. They get slightly different answers. This disagreement is called the Hubble tension, named after Edwin Hubble, the astronomer who first showed that the universe was expanding at all. Some scientists think the tension comes from measurement errors. Others believe it may point to something genuinely new, some piece of physics that our current understanding simply does not include. The cosmic microwave background has given us an extraordinary map of the early universe. It has confirmed the existence of dark matter and dark energy. It has helped us measure the age, shape, and composition of the cosmos with stunning precision. And yet, the deeper we look into that ancient light, the more clearly we see the edges of what we know. That is not a failure. It is an invitation. Every answer pulled from that faint, ancient glow has opened a new question. Every measurement has revealed a new mystery waiting just beyond the reach of our instruments. The universe is not withholding its secrets out of stubbornness. It is simply larger, stranger, and more layered than any single generation of scientists can fully grasp. And so the work continues, patient and careful, one observation at a time. And so we arrive at a quiet truth, one that is easy to overlook. But once you see it, you cannot unsee it. Everything you have ever touched is made of ordinary matter. The chair beneath you, the air moving slowly in and out of your lungs, the stars you can see on a clear night, the oceans, the mountains, the bones inside your body, all of it, every single piece of the physical world you have ever known, adds up to just 5% of the total universe. 5%. The other 95% is dark matter and dark energy. Things we cannot see, cannot touch, and cannot yet fully explain. The universe we live in, the one we can measure and name and hold in our hands, is the small part, the quiet minority, a thin layer of light floating in an ocean of the unknown. This is not a discouraging thought. It is one of the most astonishing things science has ever uncovered. Scientists arrived at this number through careful measurements of the cosmic microwave background, the ancient light left over from the early universe. By studying how that light rippled and spread across the sky, researchers could calculate exactly how much of each ingredient the universe contains. The answer came back clear. About 27% is dark matter. About 68% is dark energy. And the rest, that slim 5%, is everything made of atoms. Now think forward, not years, but billions of years. The sun will keep burning for another 5 billion years or so. When its fuel runs low, it will swell into a red giant, a star so large it may swallow the inner planets whole. Eventually, it will shed its outer layers and collapse into a white dwarf, a small, dense, faintly glowing ember. That ember will cool slowly over trillions of years. The ordinary matter of our sun will not vanish. It will simply change form, settling into something quieter and colder. Across the universe, other stars are doing the same thing on their own timelines. Massive stars will explode as supernovae, scattering the atoms they built across vast clouds of gas and dust. Those atoms will drift for millions of years and then slowly gather again, pulled together by gravity, forming new stars and new worlds. Ordinary matter keeps cycling. It transforms. It does not disappear. But dark energy does not cycle. It does not transform or scatter or gather. It simply keeps pushing. And as the universe expands, dark energy grows stronger in its effect, pulling galaxies farther and farther apart. In the very far future, perhaps 100 billion years from now, the galaxies we can see today will have drifted so far that no telescope could ever spot them. The night sky of that distant era will look almost empty. Any civilization living then will see only their own galaxy, surrounded by what appears to be a vast and featureless void. They will not know what we know now. They will not have the evidence we have gathered. The light from distant galaxies, the the clues that told us the universe was expanding will have stretched beyond detection. In a strange way, they will be more in the dark than we are. Dark matter, too, will still be there, invisible and patient. The great halos surrounding galaxies will persist long after the stars inside those galaxies have burned out. Dark matter does not age the way ordinary matter does. It does not fuse or explode or cool into embers. It simply holds its shape, a silent scaffold in the growing dark. What this tells us is something worth sitting with. The universe is not built around us. It is not built around the atoms we are made of. Ordinary matter, the stuff of stars and planets and living things, is a small and temporary flourishing inside a much larger and stranger structure. We are the brief, bright part, the spark inside the dark, and yet that 5% has done something remarkable. It has looked back at the other 95. It has measured it, mapped it, and begun to understand it. Atoms arranged into brains have reached out across billions of light years and traced the shape of something invisible. That is not a small thing. The universe gave ordinary matter just enough time, just enough light, just enough gravity to ask the deepest questions. We are here in the window, the narrow, luminous window between the hot beginning and the cold, dark, expanding future. The stars are still burning. The questions are still open. And the 5% is still looking up. And yet, for all that looking up, we should be honest about something. The models we use to describe dark matter and dark energy are our best guesses. They are careful, mathematically precise guesses, but they are still guesses. And the universe has a long history of humbling the people who thought they had it figured out. Take the Hubble constant. This is the number scientists use to measure how fast the universe is expanding. It should be a single, clean number. But when astronomers measure it one way, using the cosmic microwave background, the faint afterglow of the Big Bang, they get one answer. When they measure it another way, using the brightness of distant stars, they get a different answer. The two answers do not match. This disagreement is called the Hubble tension, and it has not gone away. It has gotten sharper as our instruments have grown more precise. something in our picture of the universe is off. We do not yet know what. Some scientists think dark energy may not be a fixed constant after all. Einstein imagined it as a steady, unchanging pressure built into the fabric of space. But new observations suggest it may shift over time. It may grow stronger or weaker as the universe ages. If that is true, then the fate of the universe we described, the slow, cold drift into darkness, may not be the right ending. The story may be different. We simply do not know yet. There is also the question of dark matter itself. Decades of searching have not produced a single confirmed particle. The detectors buried deep underground have come up empty. The collisions inside the Large Hadron Collider, the Great Particle Accelerator beneath the Swiss and French countryside, have not shaken loose a WIMP. This does not mean dark matter is not real. The gravitational evidence is overwhelming. But it may mean that dark matter is something we have not imagined yet. Something outside the models we have built. A small number of scientists have proposed a different path entirely. They suggest that maybe gravity itself behaves differently on the scale of galaxies than our equations predict. These alternative theories, sometimes called modified gravity, try to explain the rotation curves of galaxies without invoking any invisible matter at all. Most astronomers find these theories incomplete. The bullet cluster alone is very hard to explain without dark matter. But the fact that serious scientists are still asking the question tells you something. The case is not fully closed. What this means, sitting here at the edge of what we know, is that the universe is still teaching us. Every time we build a better telescope, a deeper detector, a more powerful collider, the universe hands back a new surprise. The James Webb Space Telescope, launched in late 2021, has already found galaxies in the early universe that are larger and more developed than our models predicted. Galaxies that should not exist yet by our current understanding are sitting there in the data, bright and fully formed. Dark matter is supposed to be the scaffold that lets galaxies grow. If galaxies grew faster than expected, then either dark matter behaves differently than we thought, or something else entirely was at work in those early years. This is not a failure. This is how science moves. It is slow and careful, and sometimes it finds that the map it drew does not match the territory. Then it draws a better map. We are made of atoms forged in the hearts of dying stars. The iron in our blood was born in a supernova. The oxygen in our lungs was breathed out by ancient stellar fires billions of years before our sun existed. We are the universe looking at itself, and what we are seeing is that most of what is out there, most of what holds everything together and drives everything apart, is something we cannot yet touch or name with certainty. That is a strange place to be. It is also a remarkable one. Every generation of astronomers has inherited a universe that seemed mostly understood, and every generation has discovered that the edges were far stranger than anyone expected. Dark matter and dark energy are our generation's edges. They are the horizon we are walking toward. The stars above us are still burning. The galaxies are still moving apart, carried on a tide we can measure but not explain. And somewhere in the dark, in the cold quiet between the visible things, the answers are waiting, patient and still, the way the universe always is. We are the ones in a hurry. We are the ones with questions. And the asking, it turns out, is part of what makes ordinary matter so extraordinary. And so here we are, at the quiet end of everything we have shared tonight. You have traveled a long way, from the spinning galaxies that first hinted at something hidden, to the underground detectors listening for a whisper in the dark, from Einstein's forgotten constant to the slow, steady pull of dark energy stretching space in every direction. Even now, even as you rest, you have held in your mind the idea that 95% of the universe is something we cannot see, cannot touch, and cannot yet fully explain. That is not a small thing to carry. It is, in fact, one of the most honest things science has ever admitted. There is a kind of peace in that honesty. Science is often thought of as a collection of answers. But the best scientists will tell you it is really a collection of better and better questions. Every answer opens a door. Behind that door is a room full of new mysteries, each one stranger and more beautiful than the last. Dark matter and dark energy are two of those rooms. We have stood in the doorway. We have measured the shadows on the walls. We have not yet turned on the lights. And that is perfectly all right. The universe does not mind waiting. It has been at this for nearly 14 billion years. It will still be here, slowly expanding, slowly cooling, long after every question we have asked tonight has been answered and replaced by newer, deeper ones. The galaxies will keep turning. The filaments of the cosmic web will keep stretching. The dark matter halos around each galaxy will keep holding their stars together, patient and invisible, the way they always have. Right now, somewhere in the southern sky, a galaxy called the Large Magellanic Cloud hangs like a soft smear of light above the horizon. It is a small companion galaxy to our own Milky Way. It drifts through space, wrapped in its own invisible shell of dark matter, pulled gently by the gravity of our galaxy, slowly spiraling closer over billions of years. It is a quiet dance. It has been going on longer than our sun has existed. No one is in a hurry. Everything is moving at exactly the speed it needs to move. Closer to home, our own planet is spinning right now beneath you. One full turn every 24 hours, steady and sure, the way it has been turning for 4.5 billion years. The oceans are resting under moonlight. The forests are breathing slowly in the dark. The atmosphere, that thin, warm layer of air that keeps every living thing alive, is wrapped around the earth like something careful and deliberate. And above it all, the stars are out, billions of them, scattered across a sky that is mostly empty, mostly dark, mostly made of things we are still learning to name. You are part of that sky. Every atom in your body was made in a star. The iron in your blood, the calcium in your bones, the carbon that forms the long chains of every living cell. All of it was forged in stellar fire and scattered across space before it ever became you. You are not separate from the universe. You are a piece of it that learned to wonder about itself. That is something no other piece of the universe, as far as we know, has ever managed to do. And the not knowing, the great open question of what dark matter is, what dark energy truly means, what the universe is really made of, that is not a failure. It is an invitation. Every generation gets to inherit the mystery. Every generation gets to push the edge a little further out. Somewhere tonight, a young astronomer is looking at data from a telescope and seeing something that does not quite fit. Something that nudges the edge. Something that will one day change what we think we know. That moment is coming. It always comes. The universe is endlessly generous with its surprises. For now, though, let the questions rest. Let the galaxies turn without you for a while. Let dark energy do its slow, quiet work of stretching space in every direction while you are still. The universe has been here for nearly 14 billion years. It will be here when you wake up. The stars will still be burning. The mysteries will still be waiting. And you will be ready to meet them again, rested and curious, the way all good explorers should be. The dark is not empty. It is full of things we have not yet learned to see. And that, more than anything, is a reason to keep looking. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet